PIEZOFLEX, high-performance piezoelectric flexible materials enabled by hierarchically porous graphite for application as mechanical energy harvesters and sensors. Wearable sensors that can detect and track body movements without invasively measuring them are becoming increasingly important in assessing human performance and enhancing off-site medical care and patient monitorization. Smart materials react to changes in their surroundings, making them stimuli responsive, thus being considered self-sensing and self-actuation materials, characteristics that render them extremely desirable for wearable sensors and electronics. An excellent example are the piezoelectric materials, that are the most relevant of smart materials because of important features such as cheap cost, open availability, and simplicity. Piezoelectricity is a property of materials asymmetry that causes electric impulses to be converted into mechanical force and physical information to be converted into electric signals. Due to its superior and stronger dielectric and piezoelectric characteristics, chemical stability, and easy techniques of production, barium titanate is the most widely used and researched lead-free piezoelectric. The aim of PIEZOFLEX is to investigate a completely new paradigm in engineering and expandable production of high-performance piezoelectric flexible materials. It will be composed by an upper component with graphene sheet as a current collector, an intermediate structure with clusters of piezoelectric barium titanate nanoparticles, and the base elements with strategically designed multi-level porous thin graphite, and it will be implemented in a live prototype device to harvest mechanical energy and detect motion at the end of this project. The Austin Group, represented by Dr. Donglei Fan, grew flexible porous graphite thin films with different structures. The flexible thin films were synthesized with similar procedures, utilizing chemical vapor deposition graphite growth on nickel and copper templates. All templates were etched to eliminate the nickel layer and be left with the graphite templates. The etching solution contains hydrochloric acid and iron chloride, which immerse the templates for 24 hours or longer. The graphite templates are highly hydrophobic, and to be able to grow the barium titanate particles on its surface, the template's nature had to be counteracted. Thus, the template suffered a surface treatment to become more hydrophilic. The surface treatment consisted in submerging each template in nitric acid at 50 degrees Celsius for 2 hours. The synthesis of barium titanate nanoparticles was achieved through a bottom-up method called hydrothermal synthesis, and the one implemented here is a modification of the procedure used within the Portuguese group, where the two barium titanate precursors were added to sodium hydroxide in an autoclave for 24 hours at 200 degrees Celsius. The particles were dispersed in water and tested for the ideal pH to achieve a good stability. The foam impregnation was then carried out by droplets, and this process was tested with and without the assistance of voltage that is thought to accelerate and facilitate the impregnation flow. The voltage-assisted impregnation was fulfilled with both positive and negative voltage, using a positive electrode at the top and a negative at the bottom of the foam, and vice versa. The current passing through the foam was measured while the impregnation was occurring with a steady voltage of 0.5 volts to qualify the impregnation flow. The higher the current, the deeper the particles reached. Both the etching and surface treatment processes were successful, as indicated by the foam's XRD diffractograms and by the way the particles are clinging to the foam surface, indicating that it lost its super hydrophobicity. The crystallographic phase of the barium titanate particles is a tetragonal phase, confirmed by its XRD diffractogram, which indicates possible piezoelectric behavior. The foam impregnated with no voltage exhibited a much slower impregnation flow, and there was a conglomeration of particles at the top of the foam, indicating that there wasn't an undisturbed penetration. Both voltage-assisted foams demonstrated a faster impregnation flow and fewer conglomerates at the top, demonstrating a more distributed penetration. The current measurements indicated that the negative voltage reached a higher stabilized current value at 0.28 amperes, suggesting that this voltage may be more adequate for this procedure. Nevertheless, further testing is required.